So one of the most visually interesting topics to study in physics is waves. You can think of a wave in one of two ways. You can either think of it as particles or pieces on a wave that are moving forward. So you can think of like a little piece of the wave riding the wave forward this way. Or you can think of it as an individual point in space oscillating up and down. Those are both legitimate ways of thinking about a wave, and both those kinds of waves behave in the same way. And regardless of whatever kind of wave you're working with, sound waves, light waves, seismic waves, whatever you've got, you can always think of them in terms of these four properties: frequency, wavelength, amplitude, and phase. Frequency is the number of times per second that a peak of the wave is going to pass by a certain point. So if I pick, let's say this is my point, then what I can think about is how many peaks per second pass by that point where my cursor is. That's what frequency is. Wavelength is the distance between two peaks or between two troughs in a wave. So for a large wavelength, there's going to be a lot of space between them. For a lower wavelength, there's going to be a very short distance between the peaks. Amplitude is simply how high the peaks are. So right now we've got an amplitude of 1, meaning from the center here, we go up 1 unit to get to the top of the wave, and we go down 1 unit to get to the bottom of the wave. And then phase is simply how offset the wave pattern is from sort of the center point. So if this phase were 0, we would start off with a cosine wave. So we would start out with a peak. If it were, let's see, this is in radians, so if this were equal to pi over 2, we would start out with a sine wave. But the phase doesn't really matter that much since the wave is always moving forward. The phase that you start with is not always that important. That's really going to be more important when we add waves together in the next video. So you can pretty much always leave this at 0. For this exercise, the phase, in the overall behavior of the wave, it doesn't change all that much in terms of the behavior. So then we come down here, we'll take a look at how this wave is being created. So first we're going to create this grid pattern here. You have the freedom to set how wide the grid is and how tall it is. You just make x max equal to half the width of the grid you want, because the grid's going to go from negative x max over to x max. And then y max, just make that at least 1 unit bigger than your amplitude. So if you get an amplitude of 1, give yourself a little bit of visual space there, making the amplitude 2. Then we come down here and we actually create the wave. The wave is being made using VPython's curve command. Curve is a really neat type of shape because you can make any kind of two-dimensional shape out of it. VPython stores curve as a collection of points that it then connects together with little line segments in between them. So the closer you make the points together, the smoother the curve is. Then we come down here and we add points to the wave. So whenever you have a curve function in VPython, you just use the append command, just as if you were creating a list. And we're just adding points in 3-dimensional space. So each point gets a different x coordinate. So we're just moving along the x-axis steadily here. And then here we create we use the wave function. Wave function is defined down here. You can change this if you want to. This is the generic wave function for a cosine wave. So we have the amplitude outside here, multiplying the cosine. We have 2 pi, so that we get things in terms of radians. Then we have x divided by the wavelength, minus the frequency times the time. This is the piece that makes it a wave. So if you wanted to change this function, say you wanted to change it to absolute value or something like that, this is the thing that makes it a wave. And then the phase just gets added on over here to shift it to the left or the right. Let's see, then we come down here, we're going to set the time step. I'm setting the time step here in terms of dx and the wavelength and the frequency, just so that the dt is always reasonable. So this way you don't have to worry about what the dt is. This should always keep the time step a reasonable value. And then similarly here, we're automatically setting the animation rate in terms of the time step. So this is a neat little trick you can use to always have the animation rate match with the rate of the simulation. And what I mean is, you can think of dt, the time step, as being the number of seconds in the simulation, so the number of computer seconds per frame, and the animation rate is the number of frames per real world second. So if you set animation rate equal to 1 over dt, then the animation rate is set such that a second in the real world is equal to a second in the computer world, in the simulation over here. So by setting this, you can actually use a stopwatch to actually time the period between the waves. So you'll do that in the activities at the end of this video. Then we come down here to our animation loop, and basically what we're doing is we're moving each point based on the wave function. So what we're doing is we're taking each point in the wave and we're modifying it, meaning we're moving its position. And what we're doing is we're taking this wave function, because the wave function depends both on the position that you're at. So this is a long name for the x position of the current atom in the wave, and then the time. And so as the time is changing, this x is not changing, right? Because this is fixed for each point along the wave. But then the time keeps updating with each go round of the loop, and so that changes the shape of the wave up here. And so that's why you can think of this either way, in terms of the wave moving forward or in terms of a string oscillating up and down. And so you can change lots of things about this. So like, for example, if I increase the wavelength, let's say I increase the wavelength from 1 to 3, I'm going to get much broader peaks in between the, much broader distance in between the peaks. Then if I change the frequency, let's say I make them come out more frequently, let's change that to a 2. I've got the same distance between, but they're coming more quickly. They're coming more frequently on the screen here. Then of course, if I change the amplitude, let's change that to maybe a 1.5, just so we don't get too far off the screen. Then I make the wave bigger. I'm going from 0 to 1.5, from 0 down to negative 1.5. That is moving really fast. Let's put that frequency back down to 1. And you can kind of get the idea that this frequency and wavelength has an impact on how quickly the wave moves across the screen. So that's another thing you'll figure out, is the relationship between the frequency, the wavelength, and how fast these peaks move, because that sure does look like a velocity, but we have not explicitly set a velocity anywhere up here. So let me show you one other trick you can do. You can get this wave to go backwards. You can get it to go to the left if you change two things. First, if you take this wavelength and make it negative, and then for the purpose of the code, this isn't really a physics thing, but we need to take dt and put this under an absolute value, because otherwise it thinks it's going backwards in time while it's going backwards in space, and those two backwardses cancel out. You didn't know backwards was plural, did you? But those two changes will make the wave move to the left. The wavelength's not really negative, right? Because you can still measure a length on a ruler, it will be positive. But basically, this is a little signal for the wave function down here to move backwards, because now there's implicitly a negative sign over here. You can also achieve the same effect by not making those two changes and by changing this negative into a plus. There's a few different ways to get your wave to move backwards. So anyway, I hope that is fun for you. I hope that's helpful with you as you learn about waves. Next time, we'll look about what happens when two waves meet each other. Thanks so much for watching. I will see you next time. Bye-bye.